Okay, again, today start with this formal specification in this lecture. Now you can see we talk about start this topic with a you know swinging tree, tree swing cartoon. So you can understand by seeing this cartoon. So the customer explained something and it was marketed in a different way, and the customer wants something, his requirements are something. Now when the software developed, now it is developed to the client, that is something else. Okay, this is what all through this cartoon we can see. Now formal methods, so they are actually some set of general collection of techniques, mathematical techniques. They are actually used to analyze the software requirements or the specifications. So through these formal methods, we can specify the requirements as well as we can analyze the specification for towards their correctness or the proof. We try to check the consistency. If you use these formal methods, which can help us in this transformational developments, that means once if there were any means to take the requirements and verify these requirements, I mean, if there is any mean through which if you can take the requirements and then verify those requirements, once those things can be done, so what can be done after that? So you can easily transform these requirements automatically into a piece of code. Okay, and the same sort of thing can be applied to all of the phases. As a result, what will happen? So we retain the continuity between various phases. I mean, whatever the understandings that we'll have, so that the same understanding will be carried out, that understanding will be carried out throughout all the phases. Okay, because something if you can automatically generate, or something if the requirements or something through some means, if those requirements are specified and then verified, so then usually we do not make any mistake, right? Like if the same specification has to be uh, read by various people or the various technical people, right, throughout the development of software, then there will be definitely some sort of human errors, right? But these human errors can be removed if we can go through these formal methods. Okay, because all of these requirements can be automated, and once the machine finally produced, when it produced the code, then thereafter I mean the technical people or the human being can verify that particular piece of code or the specification. Now it can be used for program verification. So checking or testing to make sure that we have built the desired ones. That means you can generate some sort of test cases automatically from the piece of specification. If the specifications through some means, if we have developed the specifications and we have verified those specifications are correct, now automatically some test cases can be generated. Okay, once if these test cases are generated, now those test cases can be used to verify the system once the software development is complete. Okay, that means during the testing phase, we try to execute these test cases. Now, these formal methods have not become a mainstream software development technique. There are certain reasons. Because the other software techniques, so they have been very successful at increasing system quality. That means the other techniques are very robust now. So because of that, so the demand for these formal methods have also been reduced. Okay, and the another problem here is so time to market. It's a very key factor, right? So you wanted to deliver that particular product very quickly to market, right? Because the market constantly changes, right? But if you going with this formal methods, what will happen? Actually, it will not reduce that time to market, because the main objective of this formal method is that it wants to develop a system or make a system without any bugs at the first go. Okay, so that means you putting more efforts at the very beginning. Okay, because you want that particular software which will be delivered to the client should not have any bugs at the first go itself. Okay, so because of that, we need a formal methods, right? That means you correctly specifying all your requirements, not leaving any single error during specification. But it will obviously take more time. So when it takes more time, so that means it will not suit to a situation where time to market is a very key factor. That is what the scope of it is limited. They are not well suited to specific user interfaces and user interactions, like it is not well suited for front-end GUI based systems, but they are very good at specifying backend system where you will be using servers, database, how the data can be retrieved, how the data can be updated into a server, right? So those sort of things can be specified properly using these formal methods, but these formal methods are not that much suited to specifying user interfaces. Okay, so this is one of the you can say this is one of the drawback. The formal methods are hard to scale up to large systems. Okay, so it is also very difficult for us to apply this particular methods to a very large systems, because it takes more time. Now, usually when you talk about any specification in the software development process, so usually this specification and design, they are inextricably intermingled. That means they are both are intermixed. Okay, so they are inseparable. Architectural design is essential to structure a specification. So that means, so in order to come up with the appropriate specification, sometimes you need architectural design also, because this is also helping us to structure our specification. Formal specifications are expressed in a mathematical notation with precisely defined vocabulary, syntax, and semantics. So through this formal, when you talk about any formal specification, that means actually you specify the requirements by using certain number of syntaxes, semantics, as well as some set of vocabulary. Okay, through those, that means you use some sort of mathematical notations to specify your requirements. When you go into some techniques, formal specification techniques, then you will be able to understand, if you do not understand as of now. Okay, what is all this vocabulary, syntax, and semantics? Because this is this is also a language actually. So you are formal specification. Okay, so there are formal specification languages. Okay, so whenever you say any language, so usually the language consists of certain things, right? If you take up any programming language, what you see? So there are some syntax, there are some vocabulary, and there are some semantics, right? Right, you can think of something like this. If you say int x semicolon, that means it is a variable declaration, right? Int x semicolon, that means here x is the name of a variable. Okay, so it has a some semantic, right? And similarly you have some syntax also. Syntax means first you need to have a data type, okay, and then you need to have a variable, and then so each and every statement in programming language should end with a semicolon, right? And the vocabulary here is the keywords, right? Int, semicolon. So these are all certain sort of vocabulary, right? So you can think of like this. So usually your formal specification languages also contain similar sort of things, right? We'll talk in later. Okay. So now usually your specification involves in any software process, okay, development process. So first thing that we go with a requirement definition, right? So these requirement definitions should be written in natural language, so they cannot be avoided. Okay, so that means requirement definition cannot be avoided, so that must be there, and you need to that should be written in natural language. Okay, because this is the first step, as we have already discussed when we are talking about the phases of software lifecycle. Requirement specification can be avoided, and straight away we can jump into formal specification, right? So usually, the requirement specification technique that we have talked in the previous lectures, like SRS, creation of SRS document and all. So what it says is you can avoid this requirement specification, okay, part. Directly you can go into formal specification step also, but it is not generally not recommended. Okay, high level design can be generated once we get into formal specification. So what we say, so once we have done the formal specification, thereafter we can generate the high level design. Okay, and different system models driven off from the system specification. Now from this high level design and further, you can go into a architectural design, and through architectural design you can get some sort of models, system models. Okay, so the system models can be one example of a system models can be the UML diagrams. In the last lecture we have seen, right, there is a sequence diagram, right? So we have seen an example of a sequence diagram, right? Through sequence diagram also we able to specify the requirements, right? So now what we are saying is, once you have derived the formal specification, you can directly go into some system model. That means you can generate some sort of diagrams like sequence diagram, or maybe collaboration diagram, maybe interaction diagram, maybe activity diagram. There are certain diagrams, right? That is what we say. For example, UML model can be generated from formal specification, and test models can also be generated, right? In order to, you can have some test models also, right? So the same thing can be explained through this particular diagram. Now you can see what we try to say here is, so this requirement definition is actually done by this is what written in a natural language, right? And it cannot be avoided because this is the very first what you say deliverable, right? If you do not have the requirements defined properly, so I think we should not move into the other phases. That is what, so it is very important. So you cannot avoid this requirement definition, right? And after this you can go to requirement specification, right? Once the requirement specification is carried out, now you can have a formal specification, right? By using formal techniques, again you can specify the requirements, right? So now what we said in the previous slide, so directly one can go from this requirement specification to the formal specification by avoiding this requirement specification. But generally we recommend that you should go through a required specification. Okay, so that's a good thing, right? So or you can directly go into formal specification. It is up to the technical people who are carrying out this sort of activities, right? And once this formal specification is carried out, right, and then that will be converted into a high level design, right? And once this high level design is created, now you can have a architectural design. From this architectural design, you can have some sort of system modeling, like, you know, you will be going to get some UML models, right? So that means whole your requirements are specified, you know, through this particular process. Okay, now here you can see requirement specification to directly you can go to architectural design. You can skip formal specification or you can skip high level design. That is what you can say. And also from formal specification, you can directly go into the system modeling also. Okay, so that is the reason why you have a cross links in between. Okay, that is what we say. So it is up to you, right? So what you want to avoid and what you want to include. So it's a standard way that you go by the boundary. Okay, so requirement definition, requirement specification, formal specification, and then high level design, and then architecture design, and then going through system modeling. So you have some sort of models through which you exactly specified your requirements. Okay, so this is the whole process of requirement specification, right? So now these specification techniques are of two types. Okay, one is a algebraic specification, the other one is a model based specification. Okay, now, part of algebraic specification, okay, the system is specified in terms of its operations and their relationships. Okay, so when you going through this algebraic approach, so usually the complete software system we are going to develop, so its requirements are specified in terms of the operations and how and what the relationships and what are the different relationships that holds among these operations, right? I mean, how in what way these different operations are executed. Okay, so that is what exactly is specified through algebraic approach. Okay, this is the way that algebraic approach works. Okay, so when you going into algebraic approach, then you will be able to understand. We'll go specific topics under this algebraic approach, then you will understand. Okay, but as of now you just understand. So each and every system is specified in terms of its operations and the relationships. So what are the different operations it has and how these operations are, you know, related to each other. Okay, in order to accomplish a particular, you know, objective or the, you know, goal. In order to achieve a goal of that particular system, so it contains certain number of operations and these operations are related to each other. So this way you can think of. Now there is a model based approach, so where the system is specified in terms of a state model. So usually these state models are constructed some mathematical constructs such as sets, sequences. So here also, you know, we define, we you know, specify the whole software system in terms of state models. Okay, and these state models are exactly developed using some sets or sequences. These are the various mathematical techniques will be used. Okay, operations are defined by modification to the system state. Now you will have certain number of operations and these operations actually will change, you know, the state will change the system's state. Okay, so when some operation is carried out, you know, it will change the state, okay, of that particular system. We'll see through an example, then you will be able to understand this. Okay, how a operation is going to change its state. Okay, and how we can use you know, set or sequences, whatever it has. Okay. Now, these formal specification languages, so there are certainly, you know, in the literature we have a certain number of techniques. Now, as I said, you under algebraic, so for sequential systems and for concurrent systems, okay, you have two different types of systems. So you have a sequential systems and you have a concurrent systems, right? So where the processes, you know, in part of sequential, so processes are executed one after the other sequentially, whereas in case of concurrent systems, so you can see there are multiple processes concurrently gets executed, right? And they do communicate with each other, right? So now this sort of system, so there are various techniques available, right? There is a large, there is a OBJ, so they are for the sequential system, and there is a Lotus for concurrent system. Similarly, under model based, so there is a JAD, there is a VDM, and there is a CSP. Okay, so CSP, there is a Patronets. Okay, now so out of all of these, okay. So now we can see, maybe we'll go into few techniques, one or two, maybe in part of algebraic, we will see large, okay, one of the one, and under model based, we can see something Petrinets, and if possible, we'll going through the JET specification, okay. So we'll take some, techniques, and we'll explain that through example, then you will be able to understand. So you understand now what is a concurrency, or the concurrent system is all about. Okay, so multiple modules working at the same times. Okay, this is a notion. Okay, so wherever you find this sort of notion that multiple modules, they are running at the same time. So usually those concurrent, concurrent systems. So now use of formal methods. So formal methods have limited practical applicability. Their application, their principal benefits are in the reducing the number of errors in the system. So their main area of applicability is mission critical system. Usually we try to use in mission critical systems because it has a, if in case if there is any fault, or because of bugs, so maybe the plane crashes. As a result, there is a, a huge consequences. So now, in order to, right, so if you wanted to have a system without any bugs at the very first go, that we should go with a formal method. That is the reason why for the critical systems, so usually we use formal methods. In this area, the use of formal method is likely to be cost effective. Okay, when you are going to develop any critical systems, okay, so in that case, if you're going through any formal methods, then it is cost effective. Okay, because the consequences of these, the consequences of any failure of these critical systems are very tough. Formal specification involves investing more effort in early phases of software development. That is what I said you, right? So usually during requirements only, you are putting more effort in specifying your requirements. I mean, you trying to have the requirements specified without any ambiguity, without without any incompleteness, right? So these are these sort of properties, right? But once the specifications are developed, okay, once the specifications are developed, now it will ease out the later phases. Okay, it will ease out the later phases, because once the specifications are developed correctly, now automatically you can transform these specifications into a design or anything, like, and automatically from the design to the piece of code that you can carry out, right? So but this is what exactly, so it takes more effort during the early phases, but it will ease out in the later phases. Okay, so this reduces requirements errors as it forces a detailed analysis of the requirements. When you're going through this formal specification, actually you will be able to reduce the number of requirement errors. Okay, as a result, so you will come up with a very quality software at the end of the day. Use of formal specification. So usually we use this formal specification to find out incompleteness and inconsistencies, as already discussed before. Um, and then through this use you can resolve these problems, right? Hence savings is made as the amount of rework due to requirement problem is reduced, because all the requirements are correctly specified. That means you will not require any rework, okay, because there are no requirement problems, right? You have no problems at the requirement level, right? So definitely, so at later point of the time customer will not ask for the revision or changes. As a result, so little less of requirement modification is required. So now these development costs, you can see the development costs with the use of this formal specification, right? So without formal specification, now you can see in the left side, and with formal specification, now you can see in the right side plots that you can see. So the first one is, so usually uh, you know you can see, um, uh, without form, I know the first one, first bar, you can see, so that is a specification. The second one is implementation and design, and the third one is that the cost, usually validation phase takes more cost, right? Then this implementation and design similarly, uh, it takes more it requires more cost than the specification, right? We know these things, but now you can see without formal specification the costs are like this. Now if you go with formal specification, now you can see definitely this specification part, the cost of specification is increased, but if you see the overall validation and implementation design, so that particular cost has been reduced, okay. So now from this, what do you understand? Now you can say definitely we put much of effort in the very early phases, but it is ease out in the later phases, okay, because of use of these formal specifications, right? Now we'll see some properties of these formal specifications, okay. So the first property here is a completeness, okay. The specification has to be complete and the user definition document will be carried over appropriately, right? So that means that your specification should be very complete, okay, right? So that means no requirements are missed out here at this point of time, okay. So everything, so then only you can say it's a good formal specification, okay. I mean that's a property of formal specification, right? So if you use this formal specification, so definitely you will achieve this completeness property, okay. And the other one is a consistent. So now, so there should not be any ambiguity in the requirements, right? So at one point of time you are saying something, at the other point of time you contradicting whatever the statement that you have said before, right? So then also the report is not consistent. So you will be able to remove this consistency if you going through this formal specification. Let's say one example you can see. One requirement is that fewer chips has to be used. Let's say if you talk about any semiconductor technology, if you talk about any semiconductor technology where something has to be developed, some system has to be developed with the use of some chips, okay. So electronic chips, right? So now one requirement is that fewer chips has to be used, that is more chips need to be put in one chip, right? So one requirement we have something like this, okay, you have to have used only fewer number of chips. When you say fewer number of chips should be used, that means what? So all of these chips should be put inside one chip, right? Then only you can achieve that. Ultimately you need to have all of these chips, right? So what you can do is, instead of having all these separate chips, so you can have all of them into a single chip, right? Now when you put all of these single chip into a single chip, which will definitely increase the power consumption, right? Now what it says is the power consumption of each chip should be lower. So this is the other requirement. So at the other end they are saying, so power consumption of chips should be reduced, okay. One end they are saying few number of chips should be used, the other end they are saying the power should be reduced, right? So that means they are actually contradicting these two things, like we have seen before also, one example, right? So, and you can refer to my previous slides on this consistency. The other example we have taken there is, temperature, power, and this sort of example, right? Now, uh, concise. The other thing is it helps us to, write the specifications or the develop the specification, using very few number of pages, right? So usually what we say is a very mid-sized project usually, runs into hundreds of pages, right? So usually this is all because of the verbs you use, right? When you use any natural language, you use many technical words, right? So because of the verbose, so usually the page increases to hundreds of pages, right? So if you going through formal specification, probably you will be able to reduce these verbose. As a result, your report will be very concise, and similarly you have a unambiguous. Okay, uh, so ambiguity will not be there. That means you should not be, you should always clear about what is your requirements, right? So you should not have the terms like, some sort of, what do you say, some sort of fuzzy sort of words should not be there, right? So if I say my system should be highly reliable, okay, I mean here the highly reliable, highly is a some sort of, fuzzy word, okay. So there can be, that you should have some sort of quantifiable measure, right? Otherwise you won't be able to define the system, right? So those sort of things should not be there when you are writing the requirements, okay. So other thing is executable, okay. So I mean, once, maybe if you have developed your all specifications, okay, specifications, now what you can do is you can directly automatically, you can convert these specifications into designs, and from these designs, okay, from these designs, now now these designs can be, converted into piece of code automatically. Now these codes can be executed directly, okay. So this is, once these, codes are executable, now those executable code is ready. Now if the designer sees, find that, everything is correct, now it can, now it can be given into the testing phase, okay. So this is the way that, so that means, with the help of this formal specification methods or the techniques, you can have some sort of, you can retain this executable property, okay. And also the other property here is reusable, right? So now, if you use any formal specification, okay, to specify any of these requirements. Now these requirements, once let's say you, for a system A, you defined a requirement, okay, you specified a requirement using formal specification. Now the same specification now can be used for other systems also. I mean, in other systems, if you have similar sort of requirements, now then you can directly you can use this formal specifications, right? That means you can reuse these specifications, okay. Now you can see here in the example, let's say you have a response time of a module, okay, that is non-functional requirement, okay. That means when a module calling another module, okay, should not take more than 50 milliseconds, okay. This is what the requirement, this is the non-functional requirement, okay. So when you call, when a module is calling to another module, so it should not take more than 50 milliseconds, right? Now this specification, once if you have developed this specification today for this particular system, okay, now the same thing can be used for other system also. When you are, let's say you developing a application, maybe you developing a website, okay. So you developing a website, there also similar sort of requirement is there. Maybe the requirement is something like this: when the client puts a request to the server should not take more than 50 milliseconds, let's say, to respond. So this can be a requirement there also, right? Now, if you develop the specification here for the other system, now the same thing can be used there, okay, without any change. Okay, so that means so once you develop something using a formal specification, that can also be used in specifying other systems as well. Okay, so that means it retains the reusability property. Now, properties of formal specification, so provides a common language for communication between clients, designer, and implementers. Okay, so that means, so when you going through any formal specification, okay, so this will be a common language between all of these people. So client, designer, as well as the coder. Okay, so they will all use the same common language, right? So common language here is a mathematical technique, right? So now, because if you see, if you use the natural language as a common language, what will happen? Because of many verbs, so people might take the same sentence in a different way. But if you use some sort of formal mathematical techniques, right, so there will not have any sort of misunderstanding, or it will not have different interpretations, because each and every syntax or the semantics will have the same meaning, okay, when you use some sort of formal specification techniques. So it has a basis in discrete mathematics. So it uses, as I told you before also, it uses some set theory or Boolean logic or predicate logic. Okay, so now let's say we'll see one example here, a library automation example. Now we'll see how these, formally how we are going to specify any of these requirements. Okay, so now let's say this example. So there are two requirements here. Okay, the first requirement is a book can either be in the stacks or unreserved or loaned out. That means if you talk about a book in a library, either that book is there in the library itself, okay, or that particular book is reserved for some purpose. Maybe you can see that book is only, that book cannot be issued, only that book is reserved for some particular person, maybe faculties. Okay, so they only, at this point of time only this book is available for only faculties. Okay, that means you can reserve something, right? Or it can be loaned out. That means that book is already issued to a student. Okay, that can be issued to a student. So these are the three possibilities of a book. So either that book will be in the stack, or it is on the reserve state, or it can be or it is loaned out to the student. Okay, it is not available currently. It is not available in the library. Okay, now the second requirement here is, if a book is in the stack or on reserve, then it can be requested. That means if the book is available in the library and it is there on the library shelf, or if it is on reserve also, like it is on reserve, then one can request that particular book. Let's say I, as a faculty, so going to a library, if that book is there in the library and it is reserved for me, let's say for example, so then I can request that particular book. If that book is loaned out, that means if the book is not there in the library, so I cannot request, right? So this is what exactly the two requirements. Now how we going to, these are the two informal statements, right? So it is written in the natural language. Now we need to, so first thing what you need to do, we need to formalize these concepts and statements. Okay, whatever these two requirement statements we have, so we need to first formalize them. Okay, and prove some theorems to gain confidence that the specification is correct. Now whatever the specification that we have given here, we need, so with the help of some theorems, okay, so we should prove that that particular specification is actually correct. Okay, that particular specification is correct. Now this is what we need to do. Okay, now we'll see first how we going to formalize these concepts and statements, right? So now the first formalization that you can see, let's say first formalize some concepts. So here now you can see S means the book is in the stack. If the book is in the stack or it is in the self of library, so that means we represent by using S. If the book is on reserve, we can represent by R. Okay. If the book is on, if the book is loaned out, or if the book is on loan, okay, so we can represent by L. The book is requested, whether if the book can be requested or not, so that can be represented through Q. So now, so the first formalism where we represent through some variables, right? S, R, L, Q. Okay. Now the second formalization here is the first requirement what we have said. So a book can either be in the stock, on reserve, or loaned out. Okay, so that means if that particular, I mean, we use here predicate logic, right? To as I told you before, so mathematical, these formal methods uses some mathematical techniques, okay, mathematical way of specifying the requirements. That is what we are doing right now. You can see, so if the book is on stock, okay, if the book is on stock, that means it is not in the reserve state, or it is not, or it is not loaned out. Okay. Now the second statement says if the book is reserved, that means at the same time, that means it is not there on the stock, or it is not loaned out. If the book is loaned out, I mean it is issued, that means that is not there on the stock, or it is not reserved. Okay, do you understand? Now the same requirement is specified using this way. So S and not of R or L, or and not of S or L. So this way, right? First, we in the first formalism we represented what all these variables, and then now you using some conjunctions and these all predicate logics. Now you can specify this requirement. Do you understand? Now the second requirement is if a book is in the stock, okay, if the book is in the stock or in the reserve, then it can be requested. That means if that book is there on the stock or it is on reserve, then only you can request. So Q is representing, I mean, book request, right? So that means if and only if the book is on the stock or reserve, then only you can request. Okay, so now this way you can formalize your requirement statements. Okay, so for any doubt, students?
So for this Q implies S or R, like it shouldn't be other way around. Like if it is on the stack or reserved, then only we can request. But
Right,
this
right,
statement
true,
is
true,
saying
true, 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 true. Okay, so that means you see what we are trying to do here is whatever the specification that we have given, okay, requirements are there. We try to see that our specification is whether it is correct or wrong. Okay, now we will prove that. Okay, we'll prove that whether this is correct or wrong. Okay, now. If this is wrong, then what you saying the now the other way you are saying, so that will also be wrong. Okay, if you change here, that will also will not hold. Okay, so we'll talk about, you will understand that in the next slide. Yeah, correct. Okay, whatever you said is that is true. Okay, so now let's say for the, as I told you, so first thing that we formalize the requirements and then we try to prove the requirement. Okay, we try to prove the requirement, okay, or the specification, whether that particular specification is correct or not through theorem. Okay, so now you see a book on loan cannot be requested the other way. Okay, as I said you, so the previous way is what? So in the previous way we have written something like this. Okay, so if that book is there on the stock or the reserve, then you can request. Okay, Now, if this book is not there on the stock, okay, or not on reserve, that means it is requested, okay, right? So the same thing is, okay, a book on loan cannot be requested. If something is, if the book is there on the loan, okay, now you need to check that whether this specification is correct or not, okay. So through these proof methods, we can correct any specification, right? So one is that a book on loan cannot be requested. If that is there on the loan, that means that book cannot be requested. Okay, if this requirement, we need to check whether this specification is correct or not. Okay, so to see this, we need to go by some sort of proof by contradiction method. Okay, you can go by proof of contradiction. Okay, method. Now, any proof of contradiction method, what we try to do is, we start out by making one assumption that the state at the very first that the statement is false. Okay, so that means whatever the statement that you have, okay, L imply not of Q, okay, we will assume that this statement is false, or it is a we'll start with a false assumption, okay, and then we try to derive a contradiction. Okay, we try to derive a contradiction. When you derive any contradiction, that means what? So you assume, you started by with the assumption that it is a false, and then you contradicted, right? That means the statement whatever you said is actually the true one. Okay, so proof by contradiction is what? You start by a negate statement, okay, and then you try to create a contradiction in that particular statement. Okay, that means, so at very first, whatever the sentence we said, so that is true. Okay, that is, this is the way that we do by, we use proof of contradiction, right? Now we'll see an example, then you will understand. So how we are going through this proof. Okay, we'll see this. Okay, so as I said you, so if the book is on loan, so it cannot be requested. Okay, now this specification we wanted to, correct, I mean, we need to prove the correctness of this statement, whether this is a correct statement or not. Okay, how we are going to do this? So we will go through the proof of contradiction, right? So proof of contradiction, as I said you, so whatever the statement that you have, so at very first you need to assume that it's a false statement, right? That means what? Whatever L imply not of Q, that means at very first you assume that it is a false. That means this true statement is falsed out by using a negation. Okay, so that means by applying negation, what you say, you make it this, you make the whole statement is a false. Okay, negation of L imply negation of Q. Now you use some sort of rewriting rule. Okay, so in predicted logic, so you can use this not of, something L imply not of Q, that can be written as like this, not of L or not of Q. Okay, so A imply B, if you have, that can be written as something like this. That can be written as negation of A or B. Okay, so this is the rule exactly we applied. So you try to rewrite that. Okay, so now what will happen? Once you got this form and you apply De Morgan's law. Okay, let's say you have something like this. Okay, not of A or B, that means what it is going to give you? Not of A or B. That means it can be written something like this, A bar and B bar. Okay, that means not of A and not of B, that can be written, right? Now we applied this De Morgan's law here. Okay, by applying this De Morgan's law, so what you get? Not of not L, that means it is going to, not of not means it is giving L only, negation of negation, it is going to the same thing, and negation of negation Q is going to give you Q. Okay, so when you apply De Morgan's law, so you get L and Q. Now by simplification, okay, by simplifying this, either you get all L or you can get Q. Okay, so in prepositional logic, okay, so there is an inference, right? Whenever you going through have proof of certain long set statements, so you can go by simplification method, right? So we use some inferences, right? So that means when you have L and Q, so you can have either L or you can have Q. okay, through simplification. That means what you say, you see, if there are two statements, if L is a statement and Q is a statement, if L is true and Q is true, then only L and Q is true, right? That means each statement is true. Do you understand? If there are two true statements, then only this will hold because A and B also true. Okay, that means so either L or you can say Q. Okay, both can be taken for when you apply simplification. Okay, you try to simplify any theorem proving. Okay, so that means instead of L and Q, I can take here L. Okay, but if you when you take L, so we know that what is that equation when it is loaned out, that means it is not in the stock or it is not in the reserve state. Okay, then only you can loan out. That means L can be replaced with not of S or R. Okay, fine. Now the same way, the simplification of step number 3, you can have what uh, you can see now you can see negation of S or R. Okay, that can again imply to Q using the simplification of step 3. Okay, so step 3 का simplification क्या है, L ले सकते हैं और you can take Q also. Okay, now what I say, so one end by taking the simplification L, you achieve a negation of S or R. Okay, now this can also imply to Q. Okay, because if you take Q also as a simplified thing, right? So if you say Q, that means something is requested, that means it should be there on the stock as well as on the reserve, then only you can request. That means you see, one end you are getting negation of S or R, the other end you are getting S or R. Okay, so now they both these two statements are contradicting. Okay, you find a contradiction. Okay, when you going through this simplification mechanism. Okay, so these two statements are contradicting each other, right? Now, so this means when you find a contradiction, that means the statement that you assumed is actually false. Okay, that means, so in turn you have the statement at very first is a true one. Okay, your contradiction is false, that means I mean your assumption is false, that means you actually saying that whatever the statement that you have is correct. Okay, so now this way you can prove. Okay, so any doubts of our students? I think I assume that you understood. Okay, okay. Now we'll see there is an alternative solution approach. So one is that proof by contradiction we have seen. Now the alternative approach can be something like this. Okay, so as you wanted to see, you see there are two requirement statements we have. One requirement statement is that the book either can be on stock or it is on reserve or it is on loaned out. Okay, the second requirement we have seen is if the book is on stock or reserved, then only you can request. That means the second statement. Now we start by this second requirement statement. Q imply S or R. Okay, we start with this formalism. Okay. Now you rewrite this. Okay, you rewrite this. Okay. So when you rewrite this, A imply B. So that means negation of Q or S or R you will get by rewriting this. Okay. And then so what you can get here is, so you can apply the rule there. Something is loaned out only when, that means when you something is loaned out, that means it is not there on stock or reserve, right? So now using this, what you can write instead of SRR, so you can write negation of L. Okay, now what is giving here, negation of Q or negation of L you are getting. Now you can apply commutative law. Okay, that means A or B can be written as B or A. Okay, that means you swap them. Okay, so that also holds. Okay, P or Q is very equivalent to Q or P. Okay, so that means negation of L or negation of Q. Now, when negation of L or negation of Q can be again rewrite by using the imply rule, you can rewrite it. Okay, negation of L imply negation of Q. That means from the second statement, okay, from the second statement, requirement statement, you can prove any other requirement specification. Okay, that means, so based upon these two requirement specifications, if you have some other specification, now that specification can be corrected out, that can be corrected out, or that can be proved, that can be proved that this statement is, this specification is correct, because we have proved from the requirement statement to the whatever the specification you want, right? So this way, you can verify any specification based up, if you're going through some mathematical techniques, so now you can specify any verification, or you can verify any specification that the specification is very correct. Okay, so this is the alternative way. So previous one is a method of contradiction, this is an alternative way. So any mechanism can be taken up to prove that the specification is very correct. Okay, now any doubts of our students? I think you understood, right?
Sir, I had one question.
Yes, ask me.
Sir, this formal specification, as you said that we are using formal language for specifying, and
Right.
the size of the file increases. So is this should be a disadvantage of the system, right? That the file size increases
How
because
it
we are
is
not.
increasing? You see how it is going to increase file size? It is not going to increase. If you, let's say, in the previous statements you have written through natural language. Okay, now you have here, you see the requirements are written something this way. Okay, what? Either it can be a stack, reserve, loaned out, right? Now these requirements are used written using natural language, right? Now these natural language, if if you use this formal method specification, always it has a unique meaning. Okay, so everybody will understand the same. If you say uh, S and not of or RL, if you say, this has the same meaning, right? But when you write the same inference for this particular requirement statement, maybe in using English, different people understand in a different way because of the many verbs will be used. Okay, so different wordings, English wordings and all, which will lead to confusion. Now you see the same requirement is written using only three simple mathematical terms. So how it is going to increase your statement? It is actually reducing.
Okay, sir. Understood.
Yes, Sa, you are going to ask something.
No, sir. This was only my doubt.
So now you see, by using mathematics, you try to reduce, make the document very concise. Okay, I mean you make it a very short document. Okay, but thing is that the problem here is, so you need to give more effort, right? You need to understand everything properly. Then only you can formalize these all in terms of mathematics, right? If you for this you need some extra effort. Okay, some extra time you need. Okay, in order to correctly specify everything, right? Because you going through many requirements and their proofs, right? So which will require some mathematical experts also, right? So now the other slide talks about specification types. Okay, so there can be of two specification. One is interface specification, that is other one is a behavioral specification. Okay, part of interface specification, what do we talk about now? How these systems are going to interact with each other. Okay, I mean, we try to specify only the interfaces, okay, of these subsystems, but not the details of those particular subsystems, right? So if there is a system, that system is consisting of various subsystems, and these subsystems are talking to each other through their interfaces. So we try to specify their interfaces, right? And behavioral specification is concentrate on the behavior of an individual subsystem. That means we try to see how a particular system is going to behave, um, you know, in according to, I mean, that is what exactly we try to specify. Okay, how a particular, individual subsystem is going to behave. Okay, or a individual module. Now, when you're going to specify any interface, so what you try to do, let's say, as I told you, that if there is a very large system, okay, which is decomposed of various subsystems, right, with some well-defined interfaces between these subsystems, right. So what you need to know, so usually um, it all deals with various operations, right? Each and every module will have what it will have. It will have certain number of operations, right? Each and every module. Now these operations can have some return type, okay, or it can take some parameters, or this particular operations will have a name very similar to the function, okay. So you have a function, so that function will have a name. It can take some parameters as well as it can return some value, okay, after computation, right? So likewise, each and every subsystem will have these many number of operations, right? Module contains different operations, right? Sum of all operational specification wrote out is the interface specification. That means interface specification is that. So if you have specified all of these operations in that particular module, that means then it is what the interface specification, right? So if there is a 5 operations in that particular module, and if you have specified at their interfaces, right? If you specified those interfaces, right? What are the return type? What is the parameters going to take that particular operation and what its name? That means you have specified the whole subsystem. Okay. So specification of subsystem interfaces allow independent development of different subsystems, right? So that means if you have specified various subsystems, now once this specification is done, what is the benefit of it? Now these modules or the subsystems, now they can be developed independently, because let's say you can think of, there is if there is a system, and this part of this system you have two subsystem A and B. Now A subsystem, once it is specified, now that can be given to a team of to a group of team members, and the B subsystem can be given to a team of another group members, right? So this way interfaces may be defined as a abstract data types or object classes, right? So usually we define these interfaces as a abstract data type, right? So when you have an abstract data type, so usually uh, you do not specify any of the internal details, right? What you specify is what are the operations it has and what its name, what it is going to return, and what parameters it is going to take, those things. Now algebraic approach to formal specification is particularly well suited to interface specification. We'll talk about this, how this is suitable for interface specification. uh, so because here part of interface, so usually it doesn't have any state, right? So part of any interface, if you add or remove something, so these sort of things will not be there, right? So that means there is a no state change, okay? So that is the reason why, so it can be well suited algebraic specification. We'll talk about that also, okay? Now there is a behavioral specification. So algebraic specification can be cumbersome when the object operations are not independent of the object state. Okay. So algebraic specification cannot be applied when these object operations as well as the object state, if they are together. Okay. So that means whenever you carry out these object operations, so that is, if that is going to change the state of the object, that means algebraic specification cannot be applied there. Okay, because if it changes the state, that means then we should specify using model based approach, right? So that is what the understanding you need to have. So model based specification exposes the system state and defines the operation in terms of changes to the state. Okay, so usually part of model based specification we see that. Okay, so they are the one going to change the state. So Z notation is a mature technique for model based specification. So Z is one of them. So we will talk about other model based specification also. It combines formal and informal description and uses graphical highlighting when representing Z specification. We'll talk about this Z specification in detail later on. So here the key points are, so formal system specification complements informal specifications. That means it will um, helps out in specifying the requirements in a better way. That means it actually complements to the I mean it adds advantages to the informal specifications. If you do not use, that means you will not get this benefit. Okay, if you go with the formal specification, that means it will helps you out in specifying the requirements in a better way. Formal specifications are precise, unambiguous. They remove areas of doubt in specification. That means it will not keep any ambiguity. Okay, so those you will be able to specify your requirements very unambiguously. Formal specification forces an analysis of the system requirements at an early stage. Okay, so because if you're going through this formal specification, okay, so that means you will have to make lots of analysis at the very beginning. Okay, so that is what we are saying. Correcting errors at this stage is cheaper than modifying delivered system, right? That means, so if you can correct all of these errors at this point of time during the specification only, then it will make the cheaper system at the end. Okay, if you leave any errors at this point of time, then which might increase the cost when the customer asks for changes. Okay, so any doubts of our students? So can I stop now the lecture? Students, am I audible?
Yes, sir.
Yes,
Yes, sir,
sir.
you are.
Yes, sir.
Uh,
Yes, sir.
okay,
Yes,
so
sir.
I
Yes, sir.
stop the recording now.